Okay, folks, good evening. I want to, the light in here is way different from the day. I wanted to go ahead and just do a quick introduction to the D latch. Now, with what I had you guys do for the SR latch, I said that there was an inherent problem with the SR latch, and I wanted you guys to step through and actually see for yourself that Q and Q bar, when we actually had a forbidden state, where basically S bar and R bar would both go low, that would actually cause the SR latch to basically produce Q and Q bar, both outputs actually being the same. We don't want that. And it's also actually kind of arduous in some ways that S bar had to be one value and R bar had to be a specific value in order to actually cause a specific set or reset or hold in memory state to actually be valid. So the thing is that with the SR latch, somebody came in and said, well, it still has some good functionality, but maybe we can actually build off of the SR latch and utilize that with a little bit extra logic in such a way that we can actually get rid, number one, of the inefficiency and the problems that come about with that SR latch. And then on top of that, maybe make the latch a little bit better. And so, here we go. We got a D latch. And the SR latch is still present. It's actually in this space right here. And so the values that we would actually have for S bar and R bar actually still exist. The little bit of logic there is still present. But with the addition of two other NAND gates as well as an inverter and also basically two different types of inputs that I'm going to talk about in just a sec, and we're going to prove it out, we're able to basically get rid of a couple of things. Number one, the forbidden state is gone. It doesn't even exist anymore. So we only have three specific states. We have a hold state in which the prior values that we want to hold in memory were held. And then we had basically the set and reset state. But instead of actually essentially having two values that we have to maneuver around and deal with, we only basically use one bit for the set and one bit for the reset. And here's how it works. So we basically have C right here. Now C, sometimes we can think of that as, we can utilize it as a clock to synchronize it if we want. But if C is 0, then it doesn't matter what D is. Basically, Q next, the next state of the output Q, would simply be no change. It just won't work. It doesn't even matter what that value would be. However, if we actually allow for C to go high, then we basically have enabled the D latch to actually do a set or reset phase based off of whatever value we use for D. And the nice thing is, instead of having the set stage as S bar being 0 or the reset stage as R bar being 0, and instead of saying R bars and S bars and all that I absolutely hate saying, it just drives me nuts. I keep thinking I'm saying the word aardvark or something. Instead of saying that stuff, we can basically just say, well, as long as C is enabled, then if D goes low, we're in reset phase, Q is 0, Q bar is flipped, so opposite. If D is high, then we're in a set phase. Q next goes high, and Q bar is the opposite. There is no forbidden state. There is no voodoo weird S bar, R bar stuff. Basically, we essentially enable the D latch to actually perform in the way that we want. And we basically just put a 1 for a set or a 0 for a reset. Brilliant. Love it. And if we just want to hold the state, well, then we just enable. We we basically put C to 0, and then everything's held in memory. Brilliant. It's just a nice way and a way simpler operation than the SR latch, and we don't have to worry about any of the issues that came about with it. But it's because we actually took the building block of the SR latch and then actually just build upon it. Let's step through these three and see if we actually can get some specific value. In fact, actually, let's just start off and see if we can actually hold a stage in which we're going to try to reset it. We're going to try reset, but we're going to keep Z as 0 and see if anything changes. Okay, let's check this out. So we have to have a prior state, and so I'm going to put basically Q prior, and then Q next. We're going to put those on the side. So here with Q prior, we're going to try to reset it, but we're going to see what happens. So we're going to leave this as 1, which means this AND gate would have a 1 right here. 0 for Q bar, because we know that there isn't a forbidden state at all. So that means 0 is going to be utilized as the input up here. So now we can actually start parsing through this logic and see if we can verify the functionality. So C for here, we're going to say is 0. Okay? C is 0. So let's see if we actually change these states. We're going to try to reset this. So I'm going to put basically D as being low, because we know that Q is high. Let's see if we can actually cause a reset action to happen. Maybe we can, maybe we can't. If we actually cause the reset to happen, we got problems. I think we'll be good. Alright, so here we have 0 being inputted to this NAND gate. Here we go, 0. Cool. Awesome. So that causes this output to go high. So 0, NAND it with 0, causes that to go high. We have a 0 now down here with the input. So that's still 0, but now we take the 0 and that inverts now to a 1. So here we actually cause 0 and 1 to actually, well, that causes an input of 1. Let's see what happens here. Well, we have 1 for Q going all the way down here. And so we have basically 1 and 1 NAND it together. Q bar is still 0. Okay. Let's see what happens to the top. 0 is still piped up. It's continuous. So 1 and 0 NAND it together gives us 1. And because of the fact that we did not enable the D latch to actually be in a set or reset phase, that it was basically holding that, no change, then we were able to basically put a hold state in which no change happens, and these two values were not only held in memory, but they were also held opposite of each other. So what I want you guys to do with the document that I sent all of you guys is go through and verify the functionality of these two states and step through it yourself and make sure that you can visually see that. All right, see you next time.